The analysis of trusses is nothing more than the application of equations of equilibrium and section cuts. It's basically just applying our tools, solving the problem. Our tools being our 3 equations of equilibrium in 2 dimensions and section cuts. So let's start out. We have a truss. Let's first check this truss for determinacy to see if we can solve it. In terms of joints, we have 1, 2, 3, 4, 5, 6 joints. So j equals 6. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 members. And we have a pin support and a roller support, which gives a pin support has a reaction in the x and y, a roller support has a reaction in the y. So we have r equal to 3. So our equation, I equals m plus r, so 9 plus 3 minus 2 times j, which is 6. 9 plus 3 is 12. 2 times 6 is 12. This equals 0. This is a determinate structure, and we can go right ahead and solve. Now, when we're solving a truss, the first step, well, before we solve the truss, we need to load the truss. So let's add some loads to the truss, and then we can start solving the truss. So we're going to have 2 loads on this truss. These loads are P and P. And we're going to say that the truss has a height equal to L, and each of the bays has a length of L. Right? What's best is to go around and label the truss so you can distinguish which member you're talking about. So I just go through and label the joints. I say A, B, C, D, E, F, circle. So I basically letter all the joints so that I can talk about what I'm working on. Now, if we look at our reactions, we have RAY, have RAX, have RFY. If we look at our external reactions, we have 1, 2, 3, and we have 3 equations of equilibrium. So right off the bat, we can go through and find out what these external reactions are. We can say that sum of forces in the x has to equal 0. 0 will equal, we have RAX acting in the x direction and nothing else. So RAX will equal 0. If we sum forces in the y, they have to equal 0. 0 will equal RAY and RFY are going up. So we'll have RAY plus RFY. And then we have 2 loads of P acting down. So minus P, minus P. You'll find that 0 equals RAY plus RFY minus 2P. Here we have one equation with 2 unknowns, so we need to move on and use our moment equation. In order to apply the moment equation, we need to make take the moments around a point. So we're going to sum the moments around A. That has to be equal to 0. So 0 equals, if we hold our finger or point A and look at all the forces that are acting through it, namely RAX and RAY, since they act through the point and have no distance, they cause no moment. So we don't need to worry about RAX or RAY. But the forces that don't act through it are the two P's and RFY. So the sum of the moments around A will equal 0. 0 is going to equal P times L. That's for the first P. Plus P times 2L for the second P. And then minus RFY times 3L. Now, you'll notice that the P's were positive and the minus RFY was negative. When summing the moments, it doesn't have to do with whether the force is going in the positive or negative x direction. It has to go with what direction it's causing the rotation. So for my sign convention, I've said that x is positive to the right, y is positive up. Moments are positive if they're acting clockwise. Okay? Now, here I have one unknown, one equation. I can solve, and I'll find that RFY will be equal to P. And if I come back to this equation, if RFY is equal to P, RAY will be equal to P. So now, using my three equations of equilibrium, I found my three reaction forces. We know RFY equals P, we knew RAY equals P, and RAX equals 0. Now, I could have told you this right off the bat because this truss has a very special property. It's called symmetry. If we look right down the middle of the truss, we see that we have both our reactions spaced an equal amount apart, and the truss is symmetric across this line. And we have two loads spaced an equal distance apart. When you have a symmetric structure, you can always just add up the total loads and divide them by 2. Let's move on, but I want to take things we saw for with it. Now, we know now all our external forces, but what we want to do is start finding out our internal forces. Now, traditionally, there are two methods that are taught in statics. One is called the method of joints, and one is called the method of sections. For the method of joints, you go around to each joint and use two equations of equilibrium to solve for all the forces in the member. For the method of sections, you make a section cut and use that to resolve your forces. I prefer to not separate them because no one actually uses one method to solve a truss. What I want you to do is be able to apply your equations of equilibrium and your section cut and solve a truss. So I'm going to go through this problem and show you how I do it, and I actually apply both methods all the time. The only time you will ever have anyone say, solve this truss with method of joints or method of sections, is if you're taking some arbitrary test somewhere that has no basis in reality. In reality, when you're given a problem, you want to solve that problem as fast as possible. And the best way to do that is with both methods. So I would just follow my method, which is application of equations of equilibrium, and get the job done and do something else that's fun. So generally, the fastest way to solve a problem is to make a section cut. So I'm going to make a section cut right through the middle, and I'm going to cut 3 members. 1, 2, 3. Conveniently, because when I cut the member, it exposes an unknown internal force. And if I cut 3 members, I get 3 internal forces, and 3 members match my 3 equations of equilibrium. So I'm going to cut this, and I'm going to go look at the left-hand side. It doesn't really matter because both sides are exactly the same. So when you make the cut, you're going to have everything that wasn't cut is going to carry over. So I have the joints. I have the load P acting up, or acting down. I have the reaction here, which we found out was P. I have a reaction here, which I found out was 0. And then everything I cut turns into an unknown force. So you just basically draw them in. This will be force BD. This will be force CD. And this will be force CE. Now, when I draw the arrows going in and out of the joints, that puts them in tension or compression. But at this point, I'm just making guesses at whether it's going to be in tension or compression. The long and short of it is, I'm going to guess the direction. If my equilibrium equation spit me out a negative answer, I know that my arrow's going in the wrong direction and I have to change it. So I'm going to make my section cut, and then I'm going to use my equations of equilibrium to solve for my unknown forces, FBD, FCD, and FCE. Now, generally the best place to start is where you can solve directly for one force. So if we try to solve forces in the y, we have FBD, and again, x and y directions, and moments that are positive. So FBD and FCE both act in the x direction, as well as FCD. If we look for forces in the y direction, we have the applied load P, the reaction force P, and FCD. If we sum forces in the y first, we'll be able to solve for FCD directly. So let's do that. If I sum the forces in the y, they have to equal 0. 0 is going to equal I have 1 P acting up, so I have a positive P. I have 1 P acting down, so I have a negative P. And then I have FCD acting up, but it's acting at a 45-degree angle. Since I made all the dimensions L, every angle in the truss is 45 degrees. This is 45 degrees. This angle here is 45 degrees. So FCD times the sine of 45. If I look and solve this, I have a positive P and a negative P, and they cancel out. So what I find is that FCD is equal to 0. So that helped me out a bunch. I applied my force in the y. If I apply my force in the x, that is equal 0. I'll have 0 equals, I know the reaction force in the x direction is 0, but I'll have minus FBD, and I'll have plus FCE. So here I have one equation, two unknowns, so I'm going to need to move on to my moment equation. Now, you can take the moment at any point in a structure, but just like when we did the reaction force and we summed it around A, we had two reaction forces acting at A. We didn't want to have to worry about those forces, so we summed it at the point where they intersected so we didn't have to consider them. That same thing works when we're doing this section cut. If we look at point C, we see we have FCD and FCE acting there, even though we found out that FCD equals 0. If we sum the moments at point C, it will get rid of a bunch of forces that we won't have to worry about, including the force P, because the force P acts through joint C as well. So if we sum the moments about point C, they have to equal 0. 0 is going to equal, so we're summing the moments here. We'll have FBD, which is causing a counterclockwise rotation, so it'll be negative. We'll say minus FBD times L. And then we'll have P causing a positive clockwise rotation. So we'll have plus P times L. And those are the only forces that are not acting directly through point C. So we'll find out that FBD is equal to P. And if we go back, we know that FBD is equal to FCE. So FCE will equal P. So by making a section cut right off the bat, we found our three forces, FCD, FCE, and FBD. Now, if we look at how all of our forces are acting, we'll find that when an arrow is pointing into a joint like FBD, that is compression. When an arrow is pointing away from a joint like FCE, that is tension. So we know that in the bottom, FCE is in tension with a force of P. So we can say P in tension. At the top, we have P in compression. In the middle, we have 0 force because it's 0. So we've evaluated 3 out of the 8 members. Now, when I made this section cut, I specifically made it through 3 members because I have 3 equations of equilibrium. Knowing the 3 members in the middle, there's no other place where I can section cut 3 members and use all 3 equations of equilibrium. So at this point, instead of looking at different sections, I'm going to look at individual joints. So I'm going to start fresh and go on to a new kind of truss and relabel everything quickly. But we know that now we know the forces in here. We have P in compression, P in tension, 0 in the middle. And we know we have a reaction force here of P, a reaction force here of P, and a reaction force here of 0. What we can do now is look at individual joints. So let's look at joint A. And when we look at a joint, we have the forces going into that joint. So we have P up, and then the members themselves become unknown forces. So AB will have unknown force, AB, and we'll have unknown force, AC. Actually, let me turn that around because I want to make FAC going into the member. Now, since we're at the joint and all the forces are acting through a single point, summing the moments has no value because summing the moments is trivial at the joint because we know all the moments are 0 because all the points act through that joint. So instead of having 3 equations of equilibrium in a joint, we have 2. We can sum forces in the X, they have to equal 0. We can sum forces in the Y, they have to equal 0. And again, this angle here, 45 degrees. So if I sum forces in the x, well, summing forces in the x we could do, but if we look at what forces act in the x, we have AB and AC. Those are both unknowns. That wouldn't directly give us a solution. But if we look at the y, we see that we have P acting in the y, FAC acts exclusively in the x direction. So if we solve sum of forces in the y first, we can solve for FAB. We sum forces in the y, it has to equal 0. 0 will equal P minus FAB sine of 45. We'll find that FAB equals 1.44 or 1.414 P. If we then sum forces in the x, it's going to equal 0 equals FAB cosine of 45 minus FAB cosine of 45 because it's going to left minus FAC. FAC will equal minus 1.414 cosine of 45, and we'll find that FAC equal to minus P. Now, this minus means that we chose the wrong direction. What it's saying is that I said FAC was going into the joint, so it was a compressive force. It is not a compressive force. I need to come back here and turn the tail around and make it a tension force. So if we go back to the truss here, we know we have P in tension, and we have 1.414 P in compression. Now, I talked earlier about the wonderful property of symmetry acting through the middle here. What's great about symmetry in this is that if we have a symmetric structure, we know all the forces in the truss from one side are mirrored on the other. So since we have P in tension here, we know we'll have P in tension here. And since we have 1.41 in compression here, we'll have 1.414 in compression here. Now, at first, symmetry can be hard to pick out, and that's okay. What you can do is do your equations of equilibrium anyway. We could solve joint F. And if you start looking at joint F and you say, well, I have P acting here, I have FDC, FDF here, I have FEF here, this is 45 degrees. Hey, this diagram looks basically like the mirror image of this diagram. You'll kind of discover that you're redoing the work you did already. So symmetry is a fun tool that can make your work simpler. The solution of trusses is nothing more than writing equations of equilibrium, summing forces in the x, summing forces in the y. The fastest way to implement this is using a section cut, and a section cut is really useful when you're cutting 3 members. If you're not cutting 3 members, a section cut isn't really useful at all. So whenever I can make a section cut and cut 3 members, I do it. Whenever I can't make a section cut and cut 3 members, I move to looking at the joints, because at the joints, you get 2 equations and you can solve for 2 separate things. Solving a truss is nothing more than writing and solving equations of equilibrium and using section cuts, writing and solving equations.